All right, hello, welcome. Thank you for joining me. This is one of 4 videos for you guys to watch while I am away this week. What we're going to get into now is we're going to change gears just a little bit. We're going to talk about a couple of applications of integration before we bounce back to series when I return later on this week. So, the first big application of integration that we're going to talk about is area between curves. I know that for most of us, back in Calc 1, we talked about area underneath a curve, and it was a relatively simple idea. Pretty much, if I give you a function, so some y equals f of x, and I say find the area underneath the function y equals f of x between x equals a and x equals b, that's something that I think most of us are able to visualize. It's going to be not necessarily the area underneath the function, but it's the area underneath the function and above the x-axis. So this area here is the area of the region that I'm talking about, and we know how we can represent that using some Calc 1 notations, Calc 1 vocabulary. We know that this is going to be the definite integral from a to b of our function f of x dx. So the small step that we take forward in Calc 2 is, instead of thinking about the area underneath a single function and above the x-axis, is now we ask the question, well, what happens if we have 2 different functions? And let's say there's some region that's bounded by those 2 functions. How do we find the area of that region? And there's a few ways that we can go about thinking about it. So I'm going to outline this 2 different ways. The first way is probably going to be a more familiar way, basically builds directly off of what you were doing in Calc 1. And then we're going to kind of reimagine an approach, and we're going to look at it in a way that's going to be more useful for us in Calc 2. So the Calc 1 way to think about an area between 2 curves is going to be, go ahead and imagine we have 2 curves, maybe some function f and some other function g. And let's let f always take on values that are greater than g. It doesn't necessarily have to be the case, but for this case, let's go ahead and think about f of x as being some function that exists up here. And let's go ahead and let's think about g of x as being some function that exists down here. It doesn't necessarily always have to be above the x-axis. So g of x can look something like this. Okay. And let's say I want to find the area bounded by f and g between x equals a and x equals b. So let's put a over here somewhere, and let's put b over here somewhere. Okay. So the area that I'm interested in is going to be this area here. So the area now bounded by these 2 functions between x equals a and x equals b. I actually think this is a pretty good picture so far. So I'm actually going to copy and paste this right now, and I will just paste it down below. I'll reference this a little bit later on, but for now, just know that we have the same picture coming up here in a few minutes. Okay, so one way that we can think about finding this area is we know how to find the area underneath f. That's not all that difficult. So the area underneath f is going to be the area below the function y equals f of x and above the x-axis. Right? Well, what we're missing there, or what we should be removing, is going to be this little bit of area under g. This little bit of area under g we don't want to account for, and we also have some additional area down here that we do in fact want to account for. So the way that we'll handle it in this case is we'll say, well, we can find the area underneath f between x equals a and x equals b. And then we can remove the area that's underneath g. Now, actually, this next step removes this area here, removes this area here, and is also going to add in this area here. So what we're actually going to be doing is we're going to be subtracting a negative area for that area right in between, and that's going to be the same thing as adding that area back in. So we have the second integral that's going to be the difference, the difference of the area underneath f and the area underneath g. Now, because we have 2 integrals both of which have the same limits of integration, both of which are integrals with respect to x, we can actually combine these two integrals into a single integral, the integral from a to b of f of x minus g of x, all with respect to x. So that's one way for us to think about the area in between two curves as a single integral. Now, that makes a lot of sense to most students coming out of Calc 1. That makes a lot of sense to early Calc 2 students. However, this reasoning isn't very useful as we continue on our journey through some more advanced applications of integration. So, one small change that we're going to make when it comes to thinking about areas between curves is going to come up down below. So we'll start off with the exact same picture. I have a function f on top, I have a function g below. I want to find the area bounded by these two functions between x equals a and x equals b. Now, here's the small change. What we're going to do is we're going to pick a value along our x-axis. So I'm going to come over here, and I'm just going to call this value x. Right? Value along the x-axis, give it the name x, real unique. So now what we can do is now I want to go ahead and I want to draw in something that we call the representative element of area. And what this is officially, it's an infinitesimally small little sliver of area. It's kind of hard to see, it's kind of hard to draw, it's kind of hard to label. So instead of just drawing in this infinitesimally small little sliver of area, what I'm going to do is I'm going to draw in a rectangle. And this little bit here, this is what we are going to call our representative element of area. It's a small sliver of area somewhere within the region that we're looking for. Right? And we can go through and we can actually label a couple things. So I want to imagine that this is in fact infinitesimally small. Your textbook and most other resources will call this a delta x, but for our purposes, just to make the notation a little bit easier, just to get to the thick of it faster, we're going to call the width of this dx. Right? So we've got this little representative element of area. We know that the width is dx. Let's go through and think about how we'd find the height of this representative element of area. Well, the height is just going to be the distance from f down to g. So it's just going to be the difference of f of x, so our function f evaluated at that x coordinate, minus g of x, so the y value at g evaluated at that x coordinate. So now what we have is we have this little sliver of area, this small piece of area. So what we can write is we can say that the area of our representative element of area, this dA, this infinitesimally small little piece of area, is going to be given by, well, the height is f of x minus g of x, and the width, we said, is dx. So what we have here is this dA represents the area of that sliver. But we're looking for the area of the entire region. So what we want to do is we want to add up all of these infinitesimally small representative elements of area, or we want to add all of these infinitesimally small areas. Well, we can't use like a finite sum to get those finite areas, but what we can do is we can integrate. So the area is going to be the integral of all of these little slivers, all these little pieces of area, starting at x equals a and going up to x equals b. Quite often you won't see people write x equals a and x equals b. I like to include that because what we're integrating with respect to here doesn't make a whole lot of sense, or at least it's not something that we're familiar with at this point. Typically we want to say, oh, if I'm integrating with respect to a, I want to integrate from a equals a to a equals b, which doesn't make a lot of sense in this case. However, when we integrate this half of our area of the representative element of area, now it makes a lot of sense to say we're just taking the height, f of x, minus g of x, multiplying it by the width, dx, and we're adding all of these areas, starting at x equals a and going up to x equals b. And what you'll notice is we end up with exactly the same formula that we got up above. So the formula that we got from kind of thinking about, hey, we have this area that we want to remove or this extra area that we want to add, we can do that, or we can take this approach where we use the representative element of area. I will admit, at this point, the representative element of area feels like it overcomplicates things. It feels kind of useless. It feels like we're just kind of doing this to make the problems feel a little bit more difficult. Trust me, this will be something that will pay dividends later on. So let's go ahead and let's take a look at an example. So example 90 from our notes says set up but do not evaluate a definite integral to find the area bounded by y equals x squared plus 2x minus 6 and y equals x. We want to go through, we want to label the height, we want to label the width, and we want to find the area of the representative element of area. All right. So I think the best place to start any of these problems is probably with a picture. So let's draw some sort of picture. Okay, so a couple of things worth noting. I could be real precise here. I could go through and I could plot points, or I could bring this up in Desmos and actually show you what the graphs of these two functions look like and talk about the areas. However, I kind of want to model how I would go about solving these problems without a calculator, without plotting a whole lot of points, and kind of getting to the thick of it as quickly as I can. So there's a few things that I want us to be aware of here. The function y equals x, I think that should be pretty easy for us to sketch. So let's go ahead and let's sketch that. So here is y equals x. Right. The next little piece that I am looking at is this x squared plus 2x minus 6. Well, I know that that's going to be a parabola. I know that it's going to be opening upwards. And I know that it's going to have a y-intercept at the point 0, negative 6. So to me, I know that it's going to take on some sort of shape like this. As far as exactly where the roots are, as far as exactly where it intersects the other graph, I don't necessarily know that at this point in the problem, but I'll just kind of put a placeholder parabola there. So now what I can see is I can see that the area that's bounded by these two curves is going to be down in this region. Is it going to be exactly this region? No, not necessarily. But this paints enough of a picture that now I can start thinking about what the top curve is going to be, what the bottom curve is going to be, what the height of my representative element of area is going to be, what the width of my representative element of area is going to be. This gives me the bulk of the information that I need to get started. All right. So since we're tasked with approaching this problem via a representative element of area, I'm going to go through and I'm going to sketch in a representative element of area. So first thing that entails is just pick an x value. I'm going to pick mine to be right here, but there's no reason why it couldn't be over here. There's no reason why it couldn't be over here. And once we have our x value picked out, I want to go ahead and I want to draw my representative element of area. I'm not sure why that happened. There we go. That's a little better. And I guess while I'm here, I should also label my parabola. So this is the parabola y equals x squared plus 2x minus 6. Okay, so we've got region, we've got representative element of area drawn. Let's go ahead and let's start labeling what we know about it. So the width of my representative element of area is going to be dx in this case. The height, well, it's going to be the top curve, which in this case was y equals x, minus the bottom curve, which is x squared plus 2x minus 6. I believe we can simplify the height. So we have x minus x squared minus 2x plus 6. So we will have a 6 is going to be positive. We'll have a minus 2x plus x, so we'll have a minus x, and we'll have a minus x squared. So that right there is going to be the height of my representative element of area. So now that we have all of that information, now we can actually go ahead and we can label the area of our representative element of area. It's going to be the top curve minus the bottom curve, which we just found is 6 minus x squared, times the width of our representative element of area, which is dx. So that right there is the area of our representative element of area. Now, to get the area underneath the curve, we need to take all of those areas and add them together via a definite integral. So it'll be an integral of 6 minus x squared dx. At this point, one thing that we have not found yet are our limits of integration. So we still don't know what our lower limit is, we don't know what our upper limit is, and because we just loosely sketched our picture, we really can't reference our picture to find our upper and lower limits of integration. However, we can do a little bit of algebra to find that. So all we need to do at this point is we just need to find where do our two curves intersect one another. So what is this x value right here? That's going to be our lower limit of integration. And what is this value up here? That's going to be our upper limit of integration. So a little bit of algebra here. We'll set our two curves, x squared plus 2x minus 6 equal to x. Well, that turns into the quadratic equation x squared plus x minus 6 equals 0. And I do believe that this factors into x plus 3 times x minus 2. So we end up with our two coordinates. X equals negative 3 is our lower limit of integration, and x equals positive 2 is going to be our upper limit of integration. So here we can go through and we can replace our unknown limits of integration with negative 3 and 2. And at this point, we have a definite integral that represents the area bounded by those two functions. All right, let's go ahead and move on to example 91. So example 91 says there are infinitely many regions bounded by y equals cosine of 2x and y equals 1. We want to set up, but do not evaluate, a definite integral to find the area of one of these regions. We want to go through, label the height, width, and the area of the representative element of area. So similar instructions to the previous problem. So let's go through. Let's begin thinking our way through it. So the first thing that we have to know here is we have to have some sort of an idea as to what the graph of cosine is going to look like. So cosine, I know, starts at 1, drops down to 0, drops down to negative 1, then changes direction, heads back up. And I know it's symmetric with respect to the y-axis, so it is going to repeat in the negative direction as well. So that right there, good enough to at least get started with the graph of cosine. Right. The next thing that we need to think about is we need to think about our other function, which is going to be y equals 1. Well, remember, cosine bounces between negative 1 and 1. So cosine is going to intersect the graph y equals 1 right at the very top of each cycle. I think I can make that line just a little bit more straight. There we go. So there's our graph of y equals 1. Now I think we can look back through the problem statement and we can realize that, oh, the area that we're looking for is going to be the area of one of these regions here. Okay, so we've got kind of picture drawn. I tend to like the way that this looks so far. We can go through, we can start thinking about our representative element of area. So pick any x value that you would like, somewhere within that region. We can sketch in our representative element of area. Like that last example, the width is going to be dx. The height in this case is going to be the top curve minus the bottom curve. Well, throughout this entire region, the top curve was y equals 1, and I just realized that's a typo, I apologize. This should be y equals 1. Our top curve is 1, and our bottom curve is this cosine of 2x. So we can finally say that the area of our representative element of area is going to be 1 minus cosine of 2x times the width of our representative element of area, dx. And we can say that the area then is going to be the definite integral of 1 minus cosine of 2x and dx. Similar to the last example, we don't have our limits of integration yet. That's something that we will have to go about finding. However, I think it's safe to say if we're looking at this region, our two curves are going to intersect when x equals 0. So we'll have our lower limit of integration being 0. The next thing that I want to find is the next time that cosine of 2x is going to be equal to 1. Well, if you think about where cosine of 2x is equal to 1, that's always going to be at either 0, at 2 pi, at 4 pi, at 6 pi, at 8 pi. So what we want is we want 2x to be the next instance where cosine is 0. So that's going to be when 2x equals 2 pi, which is going to be when x equals pi. So if we were to plot that, x equals pi would be right there where our two curves intersect once again. And here we have a definite integral that represents the area bounded by y equals 1 and y equals cosine of 2x. At least one of the areas that's bounded by those two functions. All right, a last example that we're going to look at right now is going to be example 92, which asks us to set up, but do not evaluate a definite integral to find the area of the region bounded by x equals x and g of x equals x cubed minus 3x squared plus 3x. Okay, this one is a little bit trickier. If you're not comfortable with the graph, I might advise jumping over into Desmos and looking at the graph first. But I do believe we can get through this problem without having to reference the graph. So we'll start off with our Cartesian plane again. Again, I think we know what the graph of f of x equals x looks like, so let me go ahead and sketch that. And then g of x is a strange cubic function. And if we know anything at all about cubic functions, I know that in the most general sense, a cubic function with a positive leading coefficient is going to come up, might have one turning point, go down, might have another turning point, and then head back up. So it's possible that this is not what the graph of this function looks like, but it should be pretty close. I think I can draw this so that it looks a little bit more like a function. But I think this is going to be the type of picture that we want to be dealing with, right? So what I'm seeing almost immediately here is that we don't have one top function. We have one function on top towards the left, and then we have another function on top towards the right. So we actually do change functions right at x equals 0. So let's go ahead and let's think about how we'd account for that. So what we're going to need here is we're going to need two different integrals. We're going to need one integral that handles this side, and we're going to need a second integral that handles this side. But we can go through and we can follow the same exact steps that we followed previously. Right? I think I'm going to take these slightly out of order this time. I think I'm going to find our limits of integration first, and then I want to go through and I want to set up the two integrals. So to find our limits of integration, we're going to take our two functions and set them equal to each other. So I'm going to set x equal to x cubed minus 3x squared plus 3x. And I just realized that I had forgotten to label g of x. So let me come over here and let me label my cubic function. And now what we can do is I can subtract an x from both sides. So that leaves me with an x cubed minus 3x squared plus 2x equals 0. Here we can factor out an x, and we're left with x times x squared minus 3x plus 2 equals 0. And I believe we can even factor this further into x times x minus 2 times x minus 1. And what we end up with here is we end up with x being equal to 0, x being equal to 1 and x being equal to 2. Ooh, so that changes a couple of things, right? I kind of had my picture set up almost correctly, except I do need to move a few things around. So let's go ahead and let's account for that right now. I think what this means is that now our two graphs are going to intersect here at x equals 0. They're going to intersect again at x equals 2. And they're going to intersect at x equals 1. So here's going to be 1, and here's going to be 2. So the picture was good to get us started, but I don't think it was perfectly labeled. I apologize about that. Okay, so let's go ahead. Let's see if we can use this information here to start setting up our integrals. So first of all, let me just label this 1. Let me label this 2. So the area bounded by both of these curves is going to be the area underneath curve 1, which is going to be the definite integral from x equals 0 up to x equals 1. And on that interval, it's the cubic function that's on top. So it's going to be x cubed minus 3x squared plus 3x. Then we're subtracting x off. And then to that, we're going to add the area of the second region. Well, the area of the second region is going to be the definite integral from 1 to 2. The top curve here is x, and the bottom curve is x cubed minus 3x squared plus 3x. So now what we have is we have definite integrals representing the area bounded by those two curves. And I think with that, I'm going to go ahead and leave that there for today. We will pick back up with the next video shortly thereafter. Please, if you have any questions, please feel free to ask. We'll see you in the next one. Bye.